Today I will begin with the analysis of the origin and apparent anomalies of geomagnetism. This presentation has three main objectives. First, I will describe the anomalies of the terrestrial magnetism. I will immediately try to identify some of the inconsistencies that current models present to explain or justify these apparent anomalies. And finally, I will suggest a possible explanatory model, compatible with these anomalies. As the topic is somewhat extensive, the detailed explanation of the proposed alternative model remains for a second presentation. In geomagnetism, four striking behaviors are recognized that are usually classified as anomalous, as a result of the lack of an adequate explanatory model. To describe these apparent anomalies, I will use some simple diagrams. If this is the Earth, which, as we know, has a rotational movement around an axis that defines the geographical north-south direction. It could be thought that for reasons of symmetry, the Earth's magnetic field should be aligned with this axis of rotation. However, it has been found that, although there is a magnetic axis, it is not aligned with the geographic axis. Furthermore, the magnetic axis is displaced with respect to the axis of rotation, so that both axes do not intersect at the center of the Earth. Further, constituting what is possibly the most striking anomaly of terrestrial magnetism, periodically the magnetic field reverses its north-south orientation, as indicated in the figure. Finally, this deviation from the axis of rotation does not remain constant, but suffers permanent drift, so that we can speak of traveling magnetic poles, with the additional characteristic that the displacements of the magnetic south pole are usually not symmetrical with those that suffers the magnetic north pole. Regarding the way in which the reversal of the magnetic field occurs, it can be thought that it occurs following some type of reversal path as shown in the following diagram. But reality is not like that. In reality, the reversal of polarity is not accompanied by a rotation of the magnetic field, but of a sequence that implies weakening and extinction of the field oriented in a certain way, and resurgence of the field with an inverted orientation, with progressive intensity gain. And the cycle repeats itself following the same scheme. Numerous inversions have been documented in sedimentary levels sensitive to the orientation of the magnetic field. These inversions seem to occur with an irregular frequency, so that, on average, there are between 1 and 5 events per million years, accumulating a great number of inversions in the more than 3,500 million years through which we have an adequate geological record. But nevertheless, the biggest anomaly should be considered the very existence of the Earth's magnetic field. Since the existence of the Earth's magnetic field was documented, the hypotheses regarding its origin ranged from a magnetic mountain located near the North Pole, powerful enough to extract nails from boats and generate shipwrecks in its vicinity, to the presence of an enormous permanent magnet in the Earth's core. At the present time, it is accepted that there is a huge dynamo powered by convection currents, which mobilize electrical currents, located in what is known as the outer core of the Earth. However, even modern theories find it difficult to explain the aforementioned anomalies of the Earth's magnetic field. As I already mentioned, the modern theory, as documented in Wikipedia, assumes that a gigantic dynamo that surrounds the inner core of our planet is responsible for generating the well-known geomagnetic field and for orienting the compasses in an approximate direction to the one that defines the geographic axis of rotation. However, this theory also has its limitations. It is easy to find references such as the one corresponding to the quote shown on the screen, in which paragraphs such as the following can be read. Scientists know that today the Earth's magnetic field is powered by the solidification of the planet's liquid iron core. The cooling and crystallization of the core stirs up the surrounding liquid iron, creating powerful electric currents that generate a magnetic field stretching far out into space. This magnetic field is known as the geodynamo. Multiple lines of evidence have shown that the Earth's magnetic field existed at least 3.5 billion years ago. However, the planet's core is thought to have started solidifying just 1 billion years ago, meaning that the magnetic field must have been driven by some other mechanism prior to 1 billion years ago. This situation suggests the need to develop alternative models that can justify the anomalies described at the beginning of this presentation. Let us analyze, along this line, the possibility that the Earth's magnetic field is not the result of a gigantic dynamo in the center of our planet, but the consequence of a net electrostatic charge distributed on the surface of our planet. In this case, the Earth can behave as an immense rotating sphere, electrostatically charged that, as a consequence of its rotation, would behave like an electromagnetic coil. To produce the current orientation of the magnetic field, the net charge should be negative, as shown in the image. In this way, if, due to an external cause, which we will analyze in a future presentation, the net surface charge decreases. The same happens with the intensity of the associated magnetic field, which, however, would maintain the same magnetic orientation. We would be in the case where the rotation speed is maintained but the current circulation decreases as a consequence of the availability of less net surface charge. Finally, if, as a consequence of processes on a planetary or, as we will see, of the solar system scale, the surface charge changes its sign. Since the orientation of the planetary spin is not altered, the magnetic field would have an inverse orientation to that which it had before the change of the net surface charge. In this way the compasses, like the Earth's magnetic field, would reverse their direction. For this conceptual model to be applicable to geomagnetism, a series of global assumptions or conditions must be met. First, it is necessary that the Earth be a sphere with net electrostatic charge. In favor of this possibility we can mention that there are notable atmospheric electrostatic potentials. And, also, that the Sun generates an important net positive field. This is precisely the main theme of the next presentation. On the other hand, it is important to note that, in the electrostatic model, a conductive metallic core is not required. Since the magnetic field originates from surface charges, even moons and planets without molten metal cores can generate magnetic fields. Additionally, it is necessary that the conductive areas, on the surface of the Earth, be asymmetrically distributed, in such a way that the induction currents, generated by the planetary spin, give rise to a deviation of the global magnetic field with respect to the north-south geographic axis. In accordance with this point, it is important to note that the distribution of lands and seas is asymmetric both between the northern and southern hemispheres, and within each hemisphere. Finally, the net surface charges must change from positive to negative periodically. Associated with this very important point, we will see that the solar corona, the origin of electrostatic fields at the scale of the solar system, changes its temperature periodically. In the next presentation we will analyze the generation of a huge electrostatic field by selective expulsion of electrons from the Sun's corona, the existence and characteristics of the magnetic fields on other planets, moons, and the Sun itself, some consequences of the electrostatic model, and galactic scale phenomena, among other related items.